Hello folks, StylePoint here, and today we're going to be implementing the Swish activation function. We're going to be implementing it in Python using PyTorch. But before doing that, let us first discuss Swish and how it compares to other activation functions. Okay, so here's Swish, here is its plot, and here is its formula. Swish of x is x times s of x. S here stands for sigmoid, so it's x times sigmoid of x, which of course equals x times 1 over 1 plus e to the power of minus x. This is the formula of sigmoid. Okay, looking at the plot here, plot of Swish, it may remind us of the other activation function, namely GELU, the Gaussian error linear units activation function. And to compare this to the GELU, here is the GELU plot. And we compare this to Swish, we can alternate between these two, and indeed, they look very similar. Okay, now the difference that we see here is that Swish has like a larger or like bigger dip here, and then it comes back up, while GELU still has that dip, but it's not as pronounced, it's not as large. Okay, but overall they're very similar. Speaking of formulas, it's x times s of x for Swish, and for GELU is x times CDF of x. So they're also kind of similar. We multiply x by some function in both cases, and we basically scale x by something. But because the plots, they also look very, very similar, it probably it pretty much hints us that the plot for a sigmoid of x and the plot for the CDF, or the cumulative distribution function of x, they're also similar, right? Because in both cases, we multiply x by something, and those terms, sigmoid and CDF of x, because the plots of GELU and Swish are similar, we kind of assume or expect that they're also similar, right? And to see that or check that, let's take a look at sigmoid here. And here is the cumulative distribution function, so the CDF. And indeed, they're also very similar, right? Now the CDF, it has flat upper and lower tails, and the sigmoid has smoother kind of transitions here into upper and lower tails, but overall they're very similar. So it's no wonder that the GELU and Swish, they look very, very similar to each other, because in both cases we have x multiplied by some term, and these terms here, sigmoid and CDF, their plots, they're very similar. Okay, now, because we have a lot of these similarities between Swish and GELU, they're very much alike, that results in this kind of, feature exchange in a way. So a lot of the good features that GELU provides, right, Swish also provides. So a lot of the benefits are shared. And so to list some of them, Swish, it introduces nonlinearity. And that's super cool, because otherwise we would not be able to approximate functions that are nonlinear in nature. Swish, of course, it also allows Neuron to express a strong opinion, right? A lot stronger than in a better way, I guess, than the sigmoid, right? And the reason for that is, in case of Swish, we see that for positive x's, every unique input is going to be mapped to a unique output, right? So that's like the expressiveness of Swish. But even for negative inputs, some of them are going to be mapped to a negative value. So not all of them are going to be suppressed and mapped to 0. In case of sigmoid, any fixed real input is going to be mapped onto a 0-1 interval, and that's like one of the strengths of the sigmoid. But it comes with a trade-off that it does not allow Neuron to express a strong opinion, because everything is mapped onto the 0-1 interval, and even kind of worse is that we look at the plot of sigmoid, and it's kind of like 3 different regions. It consists of 3 different regions. It has the upper tail, it has this lower tail, and then it has like this middle segment, right? So as a result, sigmoid can only answer questions or respond with answers like yes, no, and maybe in the middle we have the maybe area, right? So yes, no, and maybe. And that does not help with the expressiveness. So while sigmoid is very cool because it maps things, maps input onto a 0-1 interval, which then allows us to interpret those output values as probabilities. While that is very cool and very powerful, again, it does have this trade-off of not having neurons, not allowing neurons to express a strong opinion. In case of Swish, of course, that's not the case. This is how it looks. For positive axis, this is how it looks all the way through positive infinity. Okay, so this is how it looks, and even for some of the negative axis, it looks it has some values that are different from 0. If we compare this to the jelly, of course, they're similar. Okay, but if we compare Swish to the ReLU activation function, not all of the negative inputs are going to be zeroed out, right? So it's not going to suppress all of the negative inputs, but at some point we will get zeros because that's how a sigmoid works, right? Right here, we get a lot of zeros once we get x small enough, or once the negative x is going to have a big enough absolute value, and then because we multiply by sigmoid, we will get some zeros, but it is better than ReLU in terms of expressiveness. It's not as good in terms of performance, right? ReLU, that can be implemented using like a ternary if operator, but here we do need to do a bit more. We need to do multiplication, division, exponentiation, addition, and so forth. So it's a bit slower, but in practice, if we run this on a GPU, it's not. In practice, it's not. There's not like a huge performance difference. Okay. So to draw one more kind of parallel with GeLU, of course they are very similar, but I want to actually also emphasize the fact that this dip here is larger. Swish allows for negative inputs, for more negative inputs to be activated in a way that it's not mapped to 0, right? So that's maybe a bit of a like a expressiveness advantage over GeLU, but overall, again, they're similar because even for GeLU, the some of the negative values are going to be mapped to some other negative values, so not everything is zeroed out. Okay, so now that we discussed Swish, we can go ahead and implement it. Okay, the first thing we're going to do here is that we're going to compute the derivative of the Swish. So we need the gradient. Swish of x, we know that's x times sigmoid of x. And we need to find x times s of x prime. Now, we're going to be using this derivative of the multiplication formula, which tells us that a times b prime is a prime b plus ab prime. And applying this formula here, we're going to get x prime s of x plus x s prime x. X prime, that's 1, so that's s of x plus x times. What's the derivative of the sigmoid? Well, we know that's sigmoid times 1 minus sigmoid. If you have not watched the video on the sigmoid, please do so. There we pretty much derive the sigmoid derivative or gradient. And this is going to be multiplied by x prime as well, because that's how the chain rule works, right? So it's s of x times 1 minus s of x times whatever derivative of whatever's inside it. It's x. But we know that the x prime is 1, so we can kind of omit that. Now, we can simplify this a bit more. Now, notice that we got s of x, so sigmoid of x, plus x times sigmoid of x times 1 minus sigmoid of x. What is x times sigmoid of x? Well, that's just Swish. We can replace this with Swish of x. And there it is. That's the derivative of the Swish. And now that we know how to compute the gradient, or the derivative, we can go ahead and implement the Swish activation function. We can start with the forward method here. And the way we're going to do this is that we're going to first compute the sigmoid. So we can do sigmoid is torch.sigmoid of data. And then we can compute the Swish value. It's going to be data times sigmoid. And then we can return this. Okay. Now, what we do here is pretty much what we have here, right? We multiply x by the sigmoided x, right? By the output of the sigmoid, if it takes the data as an input, right? So we have a sigmoid here. We apply sigmoid onto data. That's that right there. So we multiply it here, and data is the x here. So we pretty much followed the formulas there. But what we also need to do here is that we need to store the sigmoid and Swish. We need to do that because we're going to be using them in the backward method. And not to do like extra computations, extra unnecessary computations. Because we're computing the sigmoid and the swish, both of them, in a forward method, we can just store them directly in a forward method without actually recomputing them. So that's going to be a bit of a performance kind of improvement here. So we can do save for backward, right? Let's save both the sigmoid and a result. And result, of course, that's the swish of x, right? And sigmoid, that's just a sigmoided input. And we know that the gradient can be expressed using sigmoid and swish. That's all we need. We don't even need the original data, right? If we use this representation, then we would use the original data. But we kind of abstracted away that representation by using swish here. Okay, so that kind of helps. Okay, now that we have stored this here, we can unpack these values using context.saved tensors in the backward method. And we can compute the gradient by saying, well, we just pretty much copy this over. And we say, okay, so S of x, what is that? That's just sigmoid. Swish of x, what is that? That's just the result. 1 minus S of x, what is that? That's 1 minus sigmoid. And finally, we multiply grad output by the grad. So that's the chain rule pretty much, right? So we multiply the gradient we got up until this point by the gradient of swish. And we're done. That's the entire implementation of the swish activation function. Okay, now let's go ahead and test this. And for testing, we're going to be using torch autograd.gradcheck. And of course, what that does is that it compares our approximations, our gradient approximations, to the numerical approximations. And if they're close enough, we're going to say that the grad check was successful, and otherwise it was not successful, and we might need to do some debugging in our code base. But let's run this now. And there it is. Grad check was successful. So grad check successful, that's awesome. That means that our implementation was good. And of course, we would have to have a lot more tests to truly verify that that's the case. But for like a simple test, this is going to suffice. Now, I also want to show you the alternative implementation of the swish activation function. Now, Torch, of course, it has the built-in swish, just like any other activation function we implemented in this video series. Torch supports them out of the box, but we didn't want to use them, right? The goal is to implement them manually from scratch. And in case of Swish, I think Torch calls it Silu. Okay, Silu is like an alternative name for Swish, but the alternative implementation I want to show you, it's also kind of implement on your own kind of an approach. We're not going to be using Torch's, implementation or whatever PyTorch provides, but we can simplify what we have here. Okay, what we can do is that we can say, okay, we're just going to import Torch. We're just going to import torch.nn as nn, inherit from nn.module, and all we're going to do is that we're going to perform inheritance and then define the forward method. We're not going to define no backward method. We're not going to pass any context. We just have self here, as you see. We don't even pass the context. We're not going to save sigmoid and result. We're not going to do this, abstraction of x times s of x. We're not going to substitute that with the swish. We're just going to do data times torch.sigmoid of data. And the reason we can do this is because what we're using here, right, in the computation, we're just using two operations, multiplication and the sigmoid. And both of them, well, in this case, we're multiplying two tensors. So the tensor multiplication, that's like a somewhat trivial operation for PyTorch, for which it knows how to compute gradients automatically. And same for sigmoid. Sigmoid is also like a built-in operation, and it knows how to compute its grading automatically. So the autograd engine that PyTorch provides, that's very powerful, and we can use it to pretty much automatically derive backward for us. Okay, and PyTorch is going to do it for us. Now, the API is going to change a bit here, though. Instead of swish.apply, apply is needed because we're doing this torch.autograd.function, and that's the API with that kind of an implementation. But in this case, we can just initialize the Swish class, if you will, and then we can run this, and we're going to get grad check successful. Okay, so this is like the alternative implementation where we don't implement everything manually, right? And the reason I wanted to show you the more like a manual implementation is that one, it's more flexible, right? And in case we need to implement some activation function that uses some operations PyTorch does not support out of the box, this would be like the go-to implementation, right? Because it allows for that flexibility of using any kind of operations here, as long as we manually implement the gradient or the backpropagation, and of course, manually compute the gradient. But in most cases, even with the custom activation functions, this approach will probably work as long as we stick to the operations that PyTorch supports out of the box. Okay, so this is going to be it for this video. I hope you enjoyed it. I hope you found it helpful and informative. If you have any questions or suggestions, please feel free to comment in the comment section. And I'm going to see you next time.